Howdy. We're going to be taking a look at 2010 number 4, which is a good example of a problem that you might encounter in the area volume realm. In 2010 number 4, we have a region R that is bounded by the curve y equals 2 root x, the horizontal line y equals 6, and the x-axis, excuse me, the y-axis, or the line x equals 0. And now they ask us to find the area of R. Because the region is bounded by fairly simple curves, it's possible to find the area of R with either vertical or horizontal rectangles. And in fact, as we work our way through parts B and C, we'll find that we are expected to have familiarity with both horizontal and vertical integration strategies. So I'm going to demonstrate finding the area of R using either the horizontal or the vertical approach. If we want to find the area of R using vertical rectangles, we're going to draw ourselves a representative rectangle and label that as with a width of dx. And the height of our element area now is going to be top curve minus bottom curve. And the top curve is 6, and the bottom curve is 2 root x, so that we have dA is equal to top minus bottom times dx. And the area will then be the sum from the first to last, from the very first x to the very last x. 6 minus 2 root x dx. We can go ahead and evaluate the interval. And for the first term, we get 6 times 9, or 54. For the last term, we have the integral of 2 times x to the 1/2, which is going to give us 4/3 x to the 3/2 from 0 to 9. 54 minus 4/3 times 27, which simplifies to 18. So the vertical rectangle strategy is fairly familiar to you guys. The horizontal rectangle strategy is equally easy, and in fact I like the interval just a little bit better. If we want to use horizontal rectangles, then we're going to put ourselves a horizontal representative element with a height of dy. And now, because everything must be in terms of y, we're going to take and solve our curve here for x as a function of y. Y over 2 is equal to root x, and therefore x is equal to y over 2 quantity squared. And we can now compute the dA as right curve minus left curve. The right curve is y over 2 squared, the left curve is 0. So that dA is equal to y over 2 squared times dy. And the area is going to be the integral from the first to last, from 0 up to y equals 6 of dA. And this integral can be done delightfully with repair. We have derivative of the inside there, and the repair constant there, so that we get 2 times 1/3 of y over 2 cubed from 0 to 6, which again simplifies to 2 times 1/3 of 27, or 18. So we have a couple of approaches that we can take here to our area. Now, as we come down to part B, they ask us to write, but do not evaluate, an integral expression that gives the volume of the solid generated when R is rotated about the horizontal line y equals 7. Let's give ourselves some room to work. And in order to visualize this properly, we want to go ahead and draw the axis y equals 7. And when R is rotated about the horizontal line y equals 7, we're going to have to take a cut perpendicular to the axis of revolution so that we can use the discs method. Notice that the shells method is not tested on the AP exam. which implies that there is going to be no situation in which you have to use shells in order to evaluate this volume. So because we're going to be using disks, then we remember that the outer radius, we might call that r as a function of x, not to be confused with the region r, is going to be the distance from the axis to the outer curve, and the small radius, little r of x, is going to be the distance from the axis of revolution to the inner curve. And so we can write that r of x is equal to curve minus axis. And here, we're going to write it actually as axis minus curve because the axis is on top, giving us a positive radius. And likewise, we have axis minus curve for the inner radius. And now our volume is going to be pi times the integral from first to last of big R squared minus little r squared dx, or pi times the integral from 0 to 9 of 7 minus 2 root x squared minus 1 squared, or you could write it as 7 minus 6 squared. Please notice that every time that we integrate with respect to x, we're going to use the x values as our limits of integration, 0 to 9. And every time we integrate with respect to y, we're going to use the y values 0 to 6 as our limits of integration. So that's part B. In part C, we are asked to find the volume of a solid. Region R is the base of a solid for each y, where y is between 0 and 6. Notice how they emphasize that to help you with your limits of integration. The cross-section of the solid taken perpendicular to the y-axis is a rectangle. Let's pause right there. Because they have said perpendicular to the y-axis, we're going to draw ourselves a cut that is perpendicular to the y-axis. And immediately we label it as dy. These cross-sections taken perpendicular to the y-axis are rectangles whose height is 3 times the length of its base in the region R. We'll write the do not evaluate and the little expression that gives the volume of the solid. So, translating what they have told us, we have this cross-section perpendicular to the y-axis like so. Now we're going to have a rectangle that is 3 times as tall as it is wide. And the length of this rectangle, we're going to borrow from the work that we did in part A. Because this curve is y equals 2 root x, therefore x is equal to y over 2 squared. And therefore the length that we have right here is going to be y over 2 squared minus 0. So that the height is now 3 times y over 2 squared, which is 3 times the length. This gives us an area as a function of y of height times width for 3 times y over 2 to the 4th power. And finally then, our volume is going to be the integral of area dy, and that's going to be the integral from the first y to the last y, 0 to 6, of 3 times y over 2 to the 4th dy. And that's our expression, and we are done. I hope this was helpful to you. It definitely is a problem that gives us some variety because we have to master integrating both in terms